Okay. For example, take an to be this interval 0, 1 over n. Okay, so a1 is 0, 1, and this contains, okay, 0, 1 over 2, right? This is a1, this is a2, 0, 1 over 3, this is a3, and goes like this, right? 0, 1 over n, this is an, right? So we have this inclusions, but these are not closed, as you know, it is clear because their complements, this is not closed because 0 is an accumulation point and 0 is not in an, therefore it doesn't contain all the accumulation points, right? So the derived set of an is 0, 1 over n, and it is not contained in an, therefore an is not closed. Maybe I should write here. Note that the derived set of an is 0, 1 over n, and this is not contained in n, and thus an is not closed. Okay, so the assumptions of the above theorem are not satisfied. We have, okay, you know, sets like this, each is non-empty and one is contained in the previous one, but they are not closed. What about the conclusion of the theorem? What about the intersection? What is this? The intersection of all of them. So this is the set of all real numbers greater than 0, less than 1 over n. So the intersection will be what? The intersection will be the set of all real numbers greater than 0 and less than all 1 over n. So this is the set of all real numbers such that x is positive and x is less than 1 over n for all n, right? For all n, 1, 2, 3. Is there such a real number which is less than all 1 over n's and still positive? Of course, no, right? This is just the empty set. Therefore, the conclusion of the theorem is not satisfied, right? Here it is empty, but it's not empty, the conclusion, but here it is empty. Empty. This is not a contradiction. Because you know, ANs are not closed. Okay. I said examples, but I don't have any example in mind other than this. Okay, let me just give this example. So this example shows that we have to make use of the fact that ANs are all closed. Okay, in the proof. Sorusu olan var mı? Any questions so far? Anlaşılmayan bir şey olursa hani hemen beni durdurun. Proof. So we have what? Let's write down. Each an is not empty, okay, for all n. Each an is closed. And an is contained, an plus 1 is contained in an for all n, right? So this is a nested sequence of closed sets, right? Each one is contained in the previous one, and none of them is empty. The idea is this. Let me draw a picture like this. So this is, let's say, A1. A2 is something like this. It is inside this A2. And then here I have A3 and so on. How we will proceed? We will proceed as follows. We have to find a point in the intersection. And I will do the following. I will choose a point from A1 and then another point from A2, another point from A3, and so on. And I will form a sequence. Okay. You see, since this is a nested set of subsets, uh, all these xn's are contained in A1, and the sequence starting from x2 is contained in A2. The sequence starting from x3, so x3, x4, x5 is contained in A3. So maybe the first couple terms are not contained in an, but after the nth term, actually, all the terms will be inside an. So we will proceed as follows. Okay, choose xn from an. I can do this because an is not empty. Okay, uh, which is possible since each an is not empty. Okay, then xn is a sequence in a1. Okay, and indeed, uh, xk is in an for all k larger than n, right? Why is that? Because because by the choice xk is in ak, but ak, since k is larger than n, this is inside ak minus 1 and goes like this up to n plus 1 and an, right? This is a nested sequence. So the bigger ones, the subsets with bigger indexes are contained in the smaller ones. So the tail of the sequence will lie inside every an. Okay, now I guess you may predict how the proof will continue. I have a sequence. Then what you do, you take the limit of this sequence, right? And to take the limit, you need to consider the accumulation point. But for the accumulation point, you need to make sure that you have an infinite set. So let's look at this set. Okay, let me give a name to this. All right, so now consider the set. Let's say, okay, let me say, what's BD xn's and from 1 to 3. So There are two cases. Either this B is finite or infinite. We have two cases. Sorry. Case 1, B is finite. This means what? This means the following. I have x1 and then x2, x3, but after some point on, this I ran out elements, so this sequence should repeat itself. So this means what? Then uh, you know uh, one of the elements here, then uh, there is some uh, constant sequence, constant subsequence, x uh, kn of xn, because since this set is finite, one of the elements of this set must be repeated infinitely many times, right? I am trying to form a sequence, let's say, from this finitely many elements. If you try to form a sequence from this set of finitely many elements, these four real numbers, then you have to use one of them infinitely many times. I just look at that subsequence, which is constant. So let's say my sequence is like this: 2, 5, 8, 5, 10, 5, 2, 5, 8, and so on. So here, this element 5 is repeated infinitely many times. So I have this constant sequence: 5, 5, 5, 5, and so on. Okay. But you see, this element, whatever that is, so this, let's say, uh, say this constant element is equal to xn 0, okay, xn 0, then this xn 0 is inside, of course this is inside an 0, it's inside an 0 plus 1, and it's because no, I should say this. Okay. Okay, this element is contained in arbitrary. Okay, then for all n, why is that? Because kn goes to infinity, right? Kn goes to infinity. Therefore, xn 0, which is equal to xkn for all n, this is in akn, but this is inside every, let's say, am, right? uh, uh, Fix some m, since Kn is going to infinity, this element, which is this element, will be here if Kn is larger than m, right? This indices gets bigger and bigger. Therefore, this element will be inside M. Therefore, we see that this constant element lies in all of them. But this means what? Hence, this element, since it lies in all of them, it lies inside this intersection. So that this intersection is empty, right? So the proof of the case where B is finite finishes this way, because one of the elements repeats infinitely many times. This means that whatever that element must lie inside all the subsets, and therefore that element must lie inside the intersection. Okay. Any questions so far? For the other direction, so for the other case is this: B is not finite, so this is infinite. Okay, but by construction, now B is of course is in A1, because everything is inside A1, right? A1 is the largest one. A2 is inside this. A3 is inside A2. A3 is inside A4. Sorry, A4 is inside A3, and goes like this. So all the sets are right here is our picture. So everything is inside A1, and A1 is bounded by assumption. Right, that was our assumption. Nerede teoremiz? A1 is bounded. So B is an infinite set contained in a bounded set, and A1 is bounded. Hence, the set B is an accumulation point. Okay. But actually, accumulation point, okay. Say x0, okay. Well, let's think about this for a while. You see, x0 here is an accumulation point of B, okay, and B is this set, x1, x2, x3, and so on, and this is an accumulation point. This means what? For any so there is a sequence converging to this x0, right? Uh, uh, Consisting of elements of this set. Actually, in every interval containing x0, there are infinitely many elements from this set, right? And I can do the following. I can form a sequence out of this converging to x0, and that sequence, okay, let me do it this way. uh, Sorry, x0. Okay, let's do it this way. Okay, x0 is an accumulation point. uh, okay, all right, is this x1, x2, x3, and so on. Now I can form a sequence, another sequence, converging to x0. How? You see, x0 is here. Take an interval of length 1. Then there is some element from this set. Actually, there are infinitely many elements from this set contained here. So I choose one of them. X and 1, let's say. And then I consider the interval of length 1 over 2. There are infinitely many elements from this set inside here. And I choose one element, let's say x and 2, so that it is inside this 1 over 2 interval of radius 1 over 2, and so that n2 is larger than n1. I can do this because, you know, this interval contains infinitely many elements from this set. So this is how I proceed. Okay, let me write it down. So n2 larger than n1. Uh, Choose. I have to do this because I don't know whether this sequence itself is convergent, right? I don't know that. So I form a sequence consisting elements of B that converges to x0. So I do this as follows. Choose x1 from this interval, x0 minus 1, x0 plus 1. I can do this because uh, x0 is an accumulation point of this, and every such interval contains infinitely many elements from this set. I should write n1. Then choose x and 2 from B. Again, these are all from B, of course, with the following property. X and 2 this time is in this interval, and n2 larger than n1. Similarly, choose x and 3 from this interval with n3 is larger than n2. I can do this because this interval contains infinitely many elements from this set. Okay, and this is an infinite set, and there are infinitely many elements from this inside this interval because x0 is an accumulation point. So this way I form a sequence. Okay, I form a sequence like this, and you see the indices gets bigger and bigger. So this way, hence we obtain we obtain a sequence, say yn with uh, uh, so y1 is just x and 1, y2 is x and 2, and so on. Okay, y3 is x and 3. So keep the notation simple. I rename all these terms with which property? You see the distance between yn and x0 is getting smaller and smaller. So yn minus x0 is less than 1 over n. So limit of yn first of all is equal to x0, because as n gets larger and larger, this distance will get smaller and smaller. What else? What else? You see, all these elements here, of course, I also do the following. I choose this elements so that they are different than, so these are distinct elements. So I have this x and so x and 2 is different than x and 1, and and 2 is larger than n1. So I choose distinct elements with this, and 3 is different than x and 2 and different than x and 1, and 3 is larger than and 2. So each time I choose a different element, and I can do this because this set B is infinite. Okay, so I can pick different elements. All right, now what else do I have? You see, all these elements are from A1, right? You see, the sequence yn lies inside A1, and yn is a sequence of distinct elements, and limit yn is x0, and thus, so this x0 is an accumulation point of this set. Okay, but A1 is closed. Why this is an accumulation point? Because there is a sequence in A1 whose terms are distinct, and it is converging to x0. Therefore, this x0 is an accumulation point of A1. But A1 is closed, and thus A1 is equal to its, actually this is contained in here, right? All the accumulation points are contained in A1. Hence, x0 is in A1. So this limit point is an accumulation point of A1, but A1 is closed. Therefore, this point must lie inside A1. However, uh, let's say, actually this sequence lies inside in every AN. Why is that? Let m be any integer. if n is larger than m, then yn, which is okay, this is in uh, then x, no, maybe I should write like this. If k is larger than m, then yk, which is x and k, but this should be inside am. Why is that? Because and k is uh, larger than k, and this is larger than m. Right, this is a subsequence. The kth element of this subsequence, right? This and k's are like you know 2, 5, 7, 8, and so on. So the kth element of this sequence and k is larger than k, and k is larger than m. But in this case, this element uh, lies in am because by the choice, right? Uh, okay. Actually, I have this. Yeah, because these are sets so that one is inside contained in the next one. So here, uh, x and k lies inside a and k, but and k is larger than m. Therefore, this is larger. This is contained in am. That's the yeah, explanation. Okay. Well, this means what? Suppose this is am. Okay. Maybe first terms of this sequence, y1 may be outside, y2 may be outside, but after some index, so yk, if m is larger than m, so ym is here, and then ym plus 1 is here, ym plus 1 is here. So after the index m, all the terms of this sequence will lie inside am. And what is the limit of this sequence? Well, when you are talking about the limit, it doesn't matter whether you start from the first element or mth element, because when you consider the limit, you don't deal with the first terms. The first finitely many terms doesn't matter. Uh, so the limit of ym yn will be inside am because since am is also closed, right? And the limit of this sequence is of course x0, right? Ym is a sequence contained in am except the first couple of terms. It doesn't matter. Whose terms are distinct and they have limit x0. Therefore, x0 is an accumulation point, but accumulation points are contained in the set am because am is closed. So maybe I write this in more detail. Now, x0, which is limit of ym, is in am prime, and since am is closed, x0 is in am prime, and this lies in am. Okay, so what we see is then x0 is inside am for all m. In particular, this x0 is inside uh, this intersection. Maybe I'll write this in the next line. X0 is in this intersection, so that this intersection is not empty. Okay, all right. And this finishes the proof. Any questions so far? You see, I mean, you shouldn't memorize the proofs, but you should just you should just learn the ideas, okay? The definitions and relations between definitions. Uh, if you just spend some time, you can, come up with an valid argument, proof for the facts you want to prove. Uh, you should just, spend some time thinking about these concepts. Okay. Evet. Ee, Not now. Yani şimdi kullanamayız. We cannot use those facts because we haven't defined what's an interior, what's exterior at the moment. But we will soon define those facts when we start, studying metric spaces. Then you can use them, but not at this moment. Okay. Uh, you should think of this as if we are playing a game and we have certain rules, okay, and then we have certain objects and certain rules, but you have to play the game with the given objects, okay. You cannot just import an object from other game. We will define each tool, you know uh, of the game, one by one, and at the moment we will just play the game with the tools we have defined and with the rules we have derived so far. Okay, but soon we will define the concepts, new tools like interior, exterior, things you have seen in previous calculus courses. But since then, till then we will not use them. Okay, we will just only use the terms, the facts, and the objects defined in the course. Tamam mı? Okay. uh, we will see later that this fact we just proved actually is something very fundamental. It's a crucial fact about compact, actually, spaces, compact sets. We will prove it in more generality. This is just a special case of it. Okay. Now let me talk about uh, limit superior and limit inferior. let me just define, what these objects are. So let an be any sequence of real numbers, be any sequence. Uh, assume that it is bounded from above. Okay. We define the following. Define uh, Bn. So find for any n, Bn is the supremum of all a k's k larger than n. So I look at the tail of the sequence, right? I look at all the terms with index larger than n, and I take the supremum. Okay, I take the supremum. Uh, then this sequence Bn is a sequence, and actually it's a decreasing sequence of real numbers. Why is that? You see, uh, B1 is the supremum of which set? It is this set. So k will be larger than 1. So it is the supremum of this A1, A2, A3, A4. It is the supremum of this. Supremum exists because An is bounded. What about B2? B2 is the supremum of a smaller set, A2, A3, A4, and so on. This is a smaller set, and clearly, the supremum of the bigger one will be larger than the supremum of the smaller one, right? So B1 is clearly larger than or equal to B2, right? If you have a smaller set, then its supremum won't be bigger than the supremum of the larger one. If you just uh, the actual proof is very simple. Why B1 is larger than this? Because you see B1 is larger than all the elements right here because it's the supremum. Therefore B1 is an upper bound for this set. Since it's an upper bound for this set, it is larger than the supremum of this set, which is B2. Okay. Similarly, B3 is the supremum of A3, A4, and so on, and therefore B3 is larger than B2. Sorry, B2 is larger than uh, B3, right? Yes. So this way, we get a sequence like this, B1, B2, B3, and so on, Bn, Bn plus 1. A decreasing sequence of real numbers. Okay. Yes. And this sequence, of course, is bounded from below. No, it's not clear, I guess, at the moment. Okay, we have this. Uh, now assume An is also bounded from below. Then and define this time Cn to be the infimum of a case k larger than or equal to n. So this time I don't take the supremums but infimums. So now Cn will be a decreasing sequence. Okay. All right. Maybe I stop here. Next time. We have this C1, C2, C3, and so on. It will go like this. Increasing. Yes, yes. Okay. All right. Increasing. Yeah, I wrote this wrong, right? C1, C2, and so on. Okay, next time I'll start from this and show the relation between convergence of AN and convergence of BN and CN. Okay. All right. Let me stop here.